So the most general representation of preparations, measurements, and transformations, and the most general form of the Born rule. And now the question is, what if you want to be more than an operationalist? So the idea of a certain kind of realist interpretation is this. Instead of saying that we have just the description of the preparation procedure and nothing more, you say instead, well, this preparation procedure puts out a system, and that system has some properties. And it's the properties of that system that are going to influence the measurement device and determine which outcome it's going to have, perhaps just probabilistically. So, so the first thing you have to do in a realist interpretation is to posit a state space, a physical state space. So you have to say, here are all the possible ways that properties the system could have, all the collections of properties the system could have. So you might think, for example, if it's a particle, you might start off by saying, well, maybe classical mechanics was right, and the state space is just position and momentum of that particle. So that would be one choice of the state space, a phase space. But in general, you could try something much more exotic to understand quantum theory. So you could have any old manifold you like of physical states. And then the idea is that if you just have knowledge of the details of the preparation procedure, that might tell you what the physical state is. But it might not. It might be, you might have a theory, a model that says, even though you know all the details of that preparation procedure, you still don't know everything about the physical state that that procedure prepares. So for example, it could be that knowing all these details, the only thing you learn about the properties of the system is that its physical state is in some subset of all the physical states. And maybe you can partition the physical states into multiple subsets. And all you learn by learning the details of the preparation procedure is which of those subsets it's in. So it's like a coarse-grained description of the system. But more generally, it could be that knowing those details of the preparation procedure only tells you the relative probabilities of different physical states of the system. So for that reason, the most general representation of your knowledge of the physical state, so here I'm going to represent the manifold of physical states just by a line for simplicity and call the physical state lambda. So the most general representation of your knowledge of that is some distribution. So it's some positive and normalized, well, technically it's a probability density if this is a continuum. And the idea is that this is what you know about lambda if you know all the details of P. Meanwhile, if you ask, how do you represent a measurement in this sort of model? As I said, it's going to be the properties of the system that are fed into the measurement device that are going to determine the statistics of the outcomes. Yes?
How do you know that representing this variable you can't see by your preparation states is lambda? How do you know that the most general way to represent it is as you've written in the top right corner? What if there was some other mathematics that could describe it?
What do you have in mind?
Something other than our standard probability.
Yeah. So one of the implicit assumptions here is we're going to assume that the right way to characterize not knowing everything about the physical state of the system is using classical probability theory, or just probability theory. I don't have to put classical in there. So we're accustomed to saying, well, if I don't know what the state is, then I assign some probabilities to the various possibilities. So maybe at the end, if you find, oh, this kind of thing doesn't work, that might motivate you to question some of those assumptions. But for the time being, I'm going to do it that way. I'm going to assume that we can just apply probability theory. It seems reasonable enough for the time being. Yes?
So looks like we have three important variables up there, mu, lambda, and psi. Could we review exactly what each variable represents? Well,
there's no psi.
Psi?
Sorry? Psi. Oh, psi. I haven't gotten around to talking about psi yet. But here, I'm not even talking about quantum theory yet. I'm saying, suppose you have an arbitrary operational theory. In fact, I really should have said that. But last week, we saw how the landscape of possible ways the world could have been, each one of those can be described by some operational theory. And all I need to do is tell you what the convex set of states are and what the cone of measurements are. And ultimately, that means that for every preparation procedure, I represent it by some vector in a real vector space. And what I'm saying is that even for those theories, a realist interpretation would say, rather than just representing the preparation procedure and just deriving statistics, we want to say that the system that preparation prepares has some properties, and we know something about those properties based on this. So these comments are generic for a realist interpretation of any operational theory, not just quantum mechanics.
But lambda represents light, and mu represents light.
Lambda represents the physical state of the system, the specification of all its properties. Mu of lambda is a probability density over those, representing the knowledge of somebody who knows the preparation procedure. And then over here, the idea is that this measurement could reveal lambda. So at best, you might do a measurement, and its outcome tells you exactly what lambda was. But again, it could be that it only gives you some coarse-grained information. It might tell you what subset of states lambda is part of. Or it could just give you partial information about lambda. So it could be that the outcome of this measurement is probabilistic given the physical state lambda. So for example, here I've sort of written down one particular 3-outcome measurement, which so each one of these, the xi, m, comma, integer lambda, is the conditional probability of getting outcome 1 in measurement m, given that the physical state of the system fed into the device was lambda. So for example, for all these values of lambda here, you'll definitely get the first outcome. There's probability 0 for the second and third outcomes. But for a value of lambda here, you have some probability of getting the first outcome, some probability of getting the second outcome, and so on. So the idea here is that that this is the most general way of representing a measurement. We sometimes call these response functions. So each one of them is a conditional probability, so it's between 0 and 1. And if I sum over all the outcomes k, then for every value of lambda, they have to sum to 1, because I always know that some outcome has to occur, no matter what the physical state I feed into the device is. And the probabilities that appear here, you can interpret one of 2 ways. You could imagine that they're just subjective ignorance. So you could say this device responds not just to what the physical state of the system you fed into it was, but maybe there are some coin flips inside the box, and the outcome actually depends on those coin flips. So it could be that these probabilities, they say, well, given only lambda, the physical state of the system, I can't tell you whether outcome 1 or outcome 2 is going to occur, but there's some coin flip inside the box that does specify it. On the other hand, it could be, you could also, if you wanted to, interpret these probabilities as objective indeterminism. You might say, this might be your model. There's no coin inside the box. There's just nothing in the world that determines which of those outcomes is going to occur. So far, I haven't committed us to either one of those interpretations. Questions about that? Good. And then finally, if we want to reproduce the predictions of an operational theory, then recall that the operational theory tells you for all your preparations and all your measurements what the statistics of outcomes for the measurement are. And so you have to be able to reproduce that using this formula. So this is just the probability of getting outcome k, given that you measured m, and given that the physical state was lambda, times the probability that the physical state was lambda, given that you prepared p, integrated over all lambda. Good. So let me note that so far I haven't said anything here that you can't do for quantum mechanics. I have not added enough assumptions to derive a no-go theorem for a realist interpretation of quantum theory. Yes?
What do you mean by no-go theorem?
A no-go theorem is a theorem that starts with some assumptions, proves a contradiction. So Bell's theorem, which we're going to see later this week, is a no-go theorem for achieving locality and realism in quantum theory. It says, here's a bunch of things you may want, and then the proof shows you can't have it. OK, let me say a couple of words, although this isn't really going to be our focus here. You might be wondering, well, how would you represent a transformation procedure within a realist interpretation? So remember, transformation procedure takes in a system, spits it out. It's deterministic. So the idea is that you're going to represent it by a transition matrix. So this is a set of conditional probabilities. So for every input physical state lambda, it specifies a distribution over output states. So for example, here's just a kind of a cartoon of a possible transition matrix. So if lambda has one of these values up here, then the distribution over lambda prime is highly peaked out here. Whereas if lambda has some low value down here, then the distribution over lambda prime is very broad. So, so that's the idea. It's just going to perhaps map lambda deterministically to some particular lambda prime. So it could just be a permutation of the physical states. But more generally, it could, for every state you input, give you a probability distribution over the output states. And again, those probabilities could be just subjective ignorance. Somebody who only knows the macroscopic details of transformation procedure might simply not know what the final state is going to be for a given initial state. Or you could imagine that they're objectively indeterministic, that there's just nothing in the world that fixes what the final outcome is going to be. And then, of course, the formula for the statistics of outcomes of some measurement that follows that transformation, given knowledge of these three procedures, is just this here. So I take the original distribution over lambda. I feed it through this transition matrix, integrating over lambda. So this gives me a distribution over lambda prime of what's coming out of this device. And then I just integrate that with the response functions of the measurement to get the final probabilities. So again, I'm describing generically what these sorts of realist interpretations look like. Later, we're going to start seeing how people have come up with particular models that achieve this sort of thing. Final case that you would probably wonder about is, what about these kinds of transformations, the ones that aren't deterministic? You do a measurement, you get an outcome, you have a different transformation for every outcome k. So it's the same sort of thing. For each of the outcomes now, you have one of these transition matrices. If you sum over k, then you need a deterministic transition matrix. So you just demand that these things be conditional probabilities. And each one of them, if I integrate over lambda prime, gives me something less than 1. But if I then sum over k, I get 1. So as I say, we're not really going to be working with these sorts of guys, but I thought you might like to just see the most general way you have to represent these things. So what I'm going to start is to try to convince you that so far I haven't added anything that prevents us from providing a realist interpretation of quantum theory. I'm going to go back to the first interpretation we saw, which I called the orthodox interpretation. So sort of the one that follows from the textbook axioms. And I'm going to present it as a realist interpretation. And I'm going to stick to the case where we're only looking at a two-dimensional Hilbert space, and we're focused on pure states and just projective measurements. So here's the idea. For the space of physical states, you postulate the surface of a sphere. So now don't confuse this with the block sphere. The block sphere, the way we've spoken about it so far, or the block ball, I should say, is the space of operational states. It's a set of states that sort of gives you a catalog of expectations for future measurements. And it tells you, here are all the things that you could expect down the road. But this space now is going to be a space of physical state, complete specifications of the properties of the system. So it's an assumption of the model that this sphere, that the block sphere, corresponds to the space of physical states. And now suppose that you are imagining the preparation procedure that prepares a spin-a-half system up along the n-hat axis. Okay, so that's your operational state. And the question is, what distribution over this sphere corresponds to that operational state? And the orthodox model says it's a delta distribution centered at n. So that's just a fancy way of saying the pure operational quantum state describes the physical state. There's nothing more to say about the physical state. It just is the pure quantum state. OK, and then if you ask, what are the response functions that correspond to a projective measurement? So say we have the measurement of spin along the m axis. So then I have the plus m and minus m states and projectors onto those. So they have to be represented by these response functions. And the response function roughly looks like this. So if this is the m axis, the response function has value 1 at the m axis, and it goes down to 0 for the axis that's orthogonal to m. That's chi m plus. And chi m minus does the opposite. I haven't drawn it here, but it would be 1 for the minus m direction, and it would go down to 0 for the plus m direction. And it falls off as a cosine. So this is the formula for that response function. So this is just the cosine of the angle between u. So u is what I was calling lambda in the previous slide. U is just the vector on that sphere that describes the physical state. And this says that this conditional probability drops off as the cosine of the angle between m, the direction you're measuring, and u, the vector describing the physical state. And so if I ask what's the probability of getting the up along m-axis outcome when I prepare to spin up along the n-axis, I just have to integrate these two guys together. Integrate over u and multiply those guys together. And that just gives me this expression here. Now, I can't remember if this was part of the tutorial problem or not. But for spins, if you ask what's the expression for the overlap of up along m vector and up along n vector mod squared in terms of the block vectors, it ends up just being this, 1/2 1 plus m dot n, where m and n are those equivalently the vector pointing to the direction in space along which the system is spinning, which is the same as its block vector. So, OK, that wasn't part of your assignment. But it's not hard to prove this. You just write down, let me just sort of make it plausible for you without doing the calculation. You write down the block sphere expression for the projector onto, say, the m hat axis. So this is the projector for spin up along m. And if I remember correctly, it's like a half identity plus 1/2 m dot sigma. And so now imagine that you take also the projector onto n hat. That's going to give you a similar expression, but with an n here. And then you use the fact that trace over sigma I, sigma j is 0 if I is not equal to j, and trace over any one of these polys squared is just, it turns out that this is, any poly operator squared is the identity operator. So this is 2. So using those identities, if you multiply this expression with a similar expression having n here, you find that only the terms that are like sigma x, and sigma y, sigma z survive. And so you're going to have something like mx times nx plus my times ny. And that's going to give you your m dot n dependence. So yeah, anyhow, so apologies you haven't seen that expression before, but it's not hard to prove. Yes?
We saw the story of quantum theory.
You saw it? OK. Good, good. Anyhow, so the idea is that because I get this expression and because of this proof, I know that this is reproducing the predictions of operational quantum mechanics. It's saying that the probability of getting the m plus outcome, given that you prepared the n plus state, is exactly what quantum theory says it is. But it gives you a particular picture of what's going on. It says the physical states are just the pure quantum states. And measurements, according to this model, are irreducibly indeterministic. That once you tell me the full physical state, where I am on this sphere, I still get probabilistic outcomes for the measurement. Yes?
But you mentioned physical states, operational states, and quantum states.
Yeah.
What is a quantum state relative to the other two?
Well, in this course, I'm taking our default interpretation of a quantum state to be just an operational state. So at the very least, we know that a quantum state does give us a catalog of expectations, right? It does specify exactly what we should expect to occur for all measurements. So in that sense, it at least plays the role of an operational state. And in other interpretations, it may play other roles as well. So here, if you look at the subset of those quantum states which are pure, they also play the role of the physical states. So the orthodox interpretation says, when you ask what's the manifold of ways the system could be physically, the answer is just the rays in Hilbert space. And that should seem sort of familiar to you, because a lot of textbooks talk about quantum mechanics in that way. They say, imagine I've prepared the physical state of the system so it's this wave function. Right? So we're sort of accustomed to thinking that once you've given me the wave function, you've just described all the properties of the system. But there's been an assumption made here, because from the perspective of what we've been doing so far, all we're really warranted in saying is that the quantum state describes the operational state. And this extra assumption that it describes the physical state is one particular way of reproducing those operational statistics. I mean, we also saw that the orthodox approach has all sorts of problems. Remember, there was that sort of tension or inconsistency between the determinism and the continuity of isolated evolution, and the indeterminism and discontinuity of collapse rule evolution. And we talked about the measurement problem. So those are all features that this sort of interpretation still has. All we've done here is sort of provide a bit more rigorous description of what this interpretation is committing itself to. But we haven't solved any of those problems. OK, so when we talked about this on the first day, we noted that one possible response to those sorts of problems, the measurement problem, the inconsistencies of the orthodox approach, was to deny that the pure quantum state did represent reality completely. So basically saying, no, it's not the case that the manifold of physical states are the pure quantum states. And I mentioned that there was two sorts of approaches that took that view. So in general, they're called hidden variable models, because they're adding something. They say the wave function's not everything. It doesn't describe the physical state completely. But some of those models still take the quantum state to be part of that complete description, even though it's not all of it. And others take it more to be merely a description of some agent's knowledge of the physical state. So I want to talk about that difference. And then I want to move on to examples of hidden variable models of each sort.
Excuse me?
Yes?
What's the relation between a realist theory and realist theories and hidden variable theories?
Well, these were kind of a bunch of ways that the realist could try to reproduce the predictions of operational quantum mechanics, as we talked about on the first day. And I've been calling all of these realist approaches to quantum theory, although I guess you could quibble over whether this is really realist or not. But I think it's probably fair to say that there's a notion of realism wherein you could include all of these. And hidden variable models are one way of achieving that kind of realism. So what sets hidden variable models apart from the others is that typically they don't try to deny the universality of unitary dynamics. They try to preserve that and just interpret it in terms of hidden variables. They don't go Everett's route of saying that we're sort of radically deceived about there being a single outcome. And they tend to, as we just saw, hold on to things like classical probability theory. All right. So the first thing I want to do is say some general words about the idea of hidden variables. So often, a physicist's first response to the idea of a hidden variable model will be that it's not really good science. Because one way of describing a hidden variable model is to say, well, there's something that by observing the macroscopic features of your experiment, you can never come to know. That's what the hidden variables are. They're hidden from us. You can never come to know them. And so a scientist's response might be, well, if there's something that you can never come to know, then aren't you really kind of doing metaphysics? Isn't it bad to talk about things that you can never come to know? So I want to talk a bit about that objection and a response to it. And so I'm going to do it by a kind of analogy. So there's this famous allegory of the cave due to Plato. And the idea is that he imagined these prisoners who were stuck in a cave and forced to look forward at a wall. And they've been there their whole lives, and so they don't know anything different. And then there are shadows of objects projected onto the wall. So it doesn't, these look like cutouts, but really in the story it's sort of three-dimensional objects. I want you to imagine these are three-dimensional objects that are casting shadows on the wall. And the idea, Plato says, is that these prisoners are likely to think that the shadows are everything. So they might think that the shadows are real. And his point was that we're like the prisoners. We think that the objects around us are real, but they're not. Anyhow, the purpose I want to put this allegory to is to imagine a prisoner scientist who sees shadows, say a whole collection of shadows, and imagine that they have some way of knowing, like maybe on Monday they only ever see the shadows of one object, and on Tuesday they see the shadows of another object. Anyhow, this prisoner says, oh, I have a theory now. I just came up with this theory which invokes a third dimension, which we've never experienced, and something called shape in 3 dimensions. And I found that I can posit a bunch of simple shapes. And what we're seeing, the particular collection of 2-dimensional shapes we're seeing, are the set of all 2D projections of this one 3-dimensional shape. And that's a theory that makes some real predictions, because there's only certain kinds of 2-dimensional aspects of a given 3-dimensional shape. And so I would say that such a prisoner would be doing good science by taking this collection of phenomena that they're seeing and being able to explain it all in terms of a relatively simple hypothesis. But note that they would be positing hidden variables by doing that, because the 3-dimensional shape of an object is something that these prisoners can never have direct access to. They'll only ever see one 2-dimensional aspect, and the others will always be hidden from them at any given time. And now imagine a second prisoner who has a similar kind of model, but also postulates something called color. And the prisoner says, oh, and this color doesn't have any effect on the shadows. In that case, you would have to say, well, that prisoner's postulated some property for the system which we can't say anything about. It has no explanatory power. It's unrelated to the shadows. It's a hidden variable, but it's a hidden variable that doesn't really do any work for you. And I think the reaction that people often have against hidden variables is because they're thinking that the hidden variables that are postulated are like the color in this example. But as long as the hidden variables that are postulated are like the shape, then I don't think that that's a valid objection, that we're postulating something we can never come to know. OK, so questions about that? Good. All right, so let me be clear on this distinction of ontic versus epistemic. So first of all, the terminology. An ontic state is a real state of affairs. An epistemic state is a state of knowledge. So ontic and epistemic come from the Greek, and it's just a convenient way of, it's nice to have some adjectives around that'll allow me to say whether something is about reality or whether it's about knowledge of reality. OK, one simple example. Suppose we're doing classical statistical mechanics. That's a place where this distinction arises and nobody argues about it. So if, for example, I'm describing a system in 1 dimension, then the physical states will be points in the phase space of that system. So a given point in this 2-dimensional manifold describes the position and momentum of the system. And according to classical mechanics, that's a complete specification of the physical properties of the system. There's nothing more to say about it. So those points are the ontic states. But in statistical mechanics, we have a second notion of state, which sometimes people call the Liouville state. And it's a distribution over this space. And you can think of that in one of 2 ways. You can think of it as, OK, that distribution describes an ensemble of systems. And the relative height at different points in that distribution is the relative frequency with which different physical states appear in that ensemble. And then the other interpretation is just, if I draw a particular element from that ensemble, it's the probabilities in that distribution are the credence I assign to the possibilities of this system being in the various physical states. So you can think of that probability distribution as a description of what I know about the physical system. I know that it's more likely to be in the state which is under the peak of this distribution than it is to be in a state way out here on the tail. And that's mostly the interpretation that I'm going to use here. There isn't much of a difference between those two. But of course, the point here is really that if I'm talking about a single system, the status of the point in this phase space and the distribution of the phase space, they have completely different statuses. One is a description of the properties of the object. The other is a description somehow of the agent's relationship with the object. What does the agent know? And no matter how hard you inspect the system, you won't find any parameters that describe the shape of this distribution, because that's not a function of the system alone. It's a function of what the agent knows about the system. Okay? So this probability distribution is not like an electromagnetic field. An electromagnetic field is also a function over a space, but it actually describes physical degrees of freedom. This is part of epistemology. It describes what we know. So it has a very different status. OK, and then a bit more terminology. Whenever I talk about an ontic parameter, then what I mean is that the real state of affairs varies with this parameter, or the ontic state varies with this parameter. So if I have some parameter that as I change it, the ontic state must change, I'll call that an ontic parameter. Whereas an epistemic parameter is one that as I change it, then some agent's state of knowledge necessarily changes. But the ontic state could stay the same. So if there's some parameter in my description of a system that I can vary, and I can leave the physical state the same, then that parameter has to describe the agent's knowledge. It can't describe reality itself. So like for example, the width of this Gaussian here is a parameter that I could vary while imagining that the physical state stays the same. So then I know that the width of that Gaussian is not describing a physical property of the system. And basically, psi-ontic and psi-epistemic models, hidden variable models, are just going to be models wherein the wave function psi is either an ontic or an epistemic parameter. OK. So I thought it might be useful to talk a little bit more about this distinction, because it's kind of critical, and it's probably not so familiar to you. So I thought what would be fun is we could have a bit of a discussion of various concepts that arise, and just talk about whether they're ontic or epistemic, or maybe there's arguments to be made for both, and why. So let me start off with the concept of probability. So let me ask you, would you say that this is more of an ontic or an epistemic concept, and why?
We saw that.
Oh, sorry. Yes?
It seems epistemic in that it can be updated discontinuously.
So on the grounds that it's when you update it, it changes discontinuously, you'd say that makes it feel more like an epistemic quantity than an ontic one.
It does, or you could say that at least in some cases it must be epistemic. There might also be ontic probability.
So what would an ontic probability be?
Somehow underlying indeterminism.
Yeah. Yes?
Well, it seems to me that if you have, say, a die and you throw it, no matter which observer is throwing it, there's a 1 out of 6 probability of getting any given outcome. So that would seem to me to be ontic in that.
You say so sometimes people use the word objective to mean something for which there will be intersubjective agreement. And so you say if everybody agrees on it, then we'll say that that's objective. So in your case, you could say, well, maybe those probabilities are objective in the sense that everybody's going to agree on them. So there's no real subjective component to it in that sense. Let me ask you this, though. So that's good, and many people argue that way. But suppose I'm rolling a dice, but I also have like a sophisticated apparatus that does a sort of a scan of it as I'm doing it and tries to measure exactly its configuration and exactly how much force I've applied to it. And suppose that that whole device allows me to predict which outcome is going to occur better than somebody who just kind of sees it. Then isn't that an example of one agent having an advantage over the others and having a different distribution? So does that kind of shake your conviction that it's objective, the fact that I can construct examples where different agents assign different probability distributions?
Well, you would have to argue then, from your point of view, that anything in the universe, like throwing a die, can always be broken down that way, where some machine sees exactly what's going on.
Well, if I wanted to claim that, I think you're right, that if I wanted to claim all probabilities were merely subjective, then I would have to be saying something like, given more information, you could do a better job, or you could maybe have a deterministic prediction rather than a probabilistic prediction.
Yeah, for every single system in the universe, which is a really strong claim.
Right. But I suppose I could potentially, there might also be room for a view where I say, there is some matter of fact about how it's going to come up. But none of us mere mortals have the capability of doing the analysis. Like maybe even the laws of physics might prevent us from learning everything we need to know about this system in order to come to know what it's going to. But I might still be able to say that there's some fact of matter in the world that determines it according to my model. And therefore, according to my model, those probabilities really are just subjective and therefore epistemic. And furthermore, we'll never be able to do better, like the prisoners in the cave who just can never see the 3D shape. Was there another hand? Yes?
A comment on what you just said.
Yeah.
So if there are those unknowable variables that make the evolution, somewhat affect the evolution deterministically, couldn't you determine them afterwards by observing the outcome? Would that still count as knowing them?
That's a good point. It could be, we can imagine different kinds of universes. I could imagine a kind of universe wherein, although I may never be able to predict the outcome of my random event, my dice roll or whatever, but maybe once it's happened, I can say retrospectively, now I know what the physical state must have been earlier. It's not useful to me anymore because the event's already happened, and the bookie won't take my bet. So that knowledge that hasn't helped me make any money at the racetrack. But I can at least say, now that the event's done, I can learn what the physical state was. Yeah. Any other thoughts on probability? Good. What about correlations? Is the notion of correlation an ontic or an epistemic concept? And I should say that, this is not a trap. You'll find people who have both sorts of views on these sorts of things. Yes?
I will suppose ontic because I would imagine everyone in the universe agreeing with a certain correlation. You cannot disagree with, some people cannot agree and disagree with the same correlation. Correlation can be proven.
So we're back to kind of something that for which there has to be intersubjective agreement should be considered ontic. And it seems you're saying that correlations are things that we sort of go out and measure and we don't really disagree about. Okay? Yes?
I'd say epistemic because if you go out and try to measure a correlation, there's some different agents, including more statistical data in their analysis of what the correlation is. You could change the direction of the correlation of the strength of it. There's those paradoxes where, like, if you include more statistical data in your analysis of correlation, then the correlation could change the strength, could change the direction.
Right. So you're referring to things like Simpson's paradox. So let me just tell everybody what Simpson's paradox is. So whether two variables are correlated or not depends on what other variables you're conditioning upon. For example, you might find that smoking and lung cancer are correlated, right? So you have a population of people, and you look at just the variable of whether they're smokers or not, and the variable of whether they develop lung cancer or not, and you find that there's this statistical correlation. But now if I look at subpopulations, and I look at the correlations within the subpopulations, and say the subpopulations are ordered, I just look at 2 of them, and it's whether these individuals have tar in their lungs or not. Well, if tar in the lungs is something that always sort of mediates the causal relationship between smoking and getting cancer, then once you told me whether or not somebody has tar in the lungs, that immediately determines whether they're going to get lung cancer or not. And so you lose the correlation with smoking, because now within the subpopulation of people who have tar in the lungs, it's kind of irrelevant whether you smoked or not. Now that you've got tar in the lungs, you're predisposed to get cancer. And Simpson's paradox basically says that if you have 2 variables, A and B, that are, say, correlated, and they become uncorrelated when I condition on C, it's always possible to dream up a probability distribution where there's some other variable, D, that I can condition on. So now I'm conditioning on C and D. And now A and B go back to being correlated. And so I can actually make a probability distribution over any number of variables such that when I condition on C, they're correlated. C and D, they're anti-correlated. C, D, and E, they're correlated again and anti-correlated again. So in that sense, that notion of correlation is something that seems to be subjective because it depends on what other things you're conditioning on, and different people might disagree on. Different people might have just different information about these other variables, C, D, and E. Yes?
So just to make sure I got this right, you're saying that originally you have a correlation between smoking and lung cancer.
Yep.
Then you find one between tar and lung cancer, and you say, therefore, the one between smoking and lung cancer has disappeared?
No, I'm saying that there's, let me just write it out explicitly, that there's 2 kinds of probability distributions I can look at. So let me make it abstract, and then I'll make it more. So suppose A, B, and C are each binary variables. They take 2 outcomes. So I can ask about the correlation between A and B in this distribution. And I'm basically asking, is it the case that this thing factorizes into PA times PB? So this actually is the technical definition of uncorrelated. If the joint distribution of 2 variables is the product of the distributions, then I say they're uncorrelated. So for them to be correlated means that this is not equal. But now I can also look at the probability of A and B given C. So let me say, like, given that you know that C has value 0, for instance, does this factorize into this and this? So in my example, A and B are smoking, lung cancer, and this is tar. And the idea is that smoking and lung cancer are correlated. So this is an inequality. Whereas if I tell you, look at the subpopulation that has tar in their lungs, so that's this side, and now ask about correlations, and now I'm computing a different probability, I find that I do get them to be uncorrelated. So how do we resolve this tension between what seems to be, on the one hand, the fact that correlations are things we can measure, and on the other hand, they seem to be subjective? Yes?
Could you just make your statements objective by including a specification of all the data you used?
So you're saying that once you specify what you're conditioning upon, then the correlations are objective?
Yeah.
Yep. Other thoughts? Yes?
Yeah, I agree with that. And or also to say and see if you agree that, well, in principle, I suppose somebody could try to say the same about probability, saying that once you say what information you have, that then the probability becomes also the same class of something. This because now it's fixed.
Mm-hmm.
I suppose it's not fixed because that seems to be the difference between probability and correlation, in the sense that once you know what information you're basing the correlation on, it's mathematically fixed. Whereas once you know the information of your system, still there is no absolute notion of probability. There's always this reasonableness that you have to, and like if you have, for example, you have to posit yourself that, if say you have no information about the die, then you posit yourself that every outcome is equally likely, and that is something you put in yourself. Whereas you don't have to do that for correlation.
So I should say that there's a big debate in the on the interpretation of probability theory, and some of this debate is because people aren't really agreed on how to interpret correlations or probability. Let me just mention that there's a position sometimes called objective Bayesianism, which manages to grant that there can be intersubjective agreement on some probability distribution, but still claim that it's epistemic. So for example, E.T. Jaynes, who is an American physicist, addressed a problem that Bayesians tend to have, which is called the problem of priors. Like if you want to use Bayesian inference, kind of to get off the ground, you have to start with a probability distribution and then update it. And the question is, well, how do you know what probability distribution to start with? What constrains your starting distribution? And subjective Bayesians say, well, that's kind of up to you. You can do what you want. It depends on what you know. And Jaynes wanted to argue, no, there are some well-defined principles. So for example, the maximum entropy principle, sometimes called the max-ent principle, says, let's say you know the expectation value of some variables. What you should do is assign the probability distribution which agrees with that expectation value, and furthermore maximizes the entropy of the distribution among all distributions that agree with that expectation value. And the idea was that the entropy is a quantitative measure of how much uncertainty you have. And Jaynes was basically saying, look, if you just know one expectation value of a variable, then you should just imagine, you should be as pessimistic as possible. You should assign that distribution which makes you as uncertain about the state of affairs as possible, consistent with your knowledge. Because anything else would be sort of presuming too much. You don't know the expectation value of any other variables. So why should you assign a distribution that claims that you're more certain than you think you are? So he argued we should maximize the entropy. And that means that if two different agents both just know the same expectation value, they're going to assign the same distribution because they're both going to follow this principle of rationality, the max-ent principle. But Jaynes would say that doesn't mean that these probabilities suddenly become objective. They're still epistemic. They're still describing those observers' ignorances. It's just that every observer uses the same set of kind of rational rules. The subjective Bayesians argue that those sorts of principles don't really work. Anyhow, so there's definitely a long debate about these sorts of issues. All right, let's try to get to the end of this list. What about determinism? So we often hear about determinism in physics. Is that an ontic or an epistemic concept? And let me see if I can hear from somebody who hasn't already spoken. Yes?
In some ways it can seem ontic because if the system evolves deterministically, then it evolves in a certain way regardless of what anyone knows. In determinism.
Yeah. One way you could describe determinism ontically is you could say something like, for every possible physical state at time t, there's a unique physical state at some later time. Seems like I haven't had to refer to any agents or their knowledge. Anyone want to defend the epistemic notion of determinism?
But doesn't the Liouville distribution work deterministically?
That's true.
And that's the epistemic state.
So where does that leave us then?
Well, I'm not sure.
Well, one thing you could say is that if you're talking about whether an evolution is deterministic or indeterministic, then that category of distinction can be applied to both ontic and epistemic concepts. So a physical state could evolve deterministically or indeterministically. but so could an epistemic state. It's just a question of whether the final state depends uniquely on the initial state or not. Anyone else? Is anybody familiar with Laplace's definition of determinism? No? So if you look at probably the first definition of determinism due to Laplace, he was sort of looking at Newton's theory. He described it this way. If you had a sufficiently powerful being who could come to know the positions and velocities of all the particles in the universe, then for it, both the future and the past would hold no mystery. That being would be able to predict everything about the future and the past. And so what's interesting about that definition, which now that I've said it, maybe it sounds familiar to you, is that it's referring to an agent's knowledge. It's trying to define determinism via an epistemic concept. It says, there's no uncertainty about the future or the past based on complete knowledge of the state, then we say that dynamics is deterministic. So I think these things can be confusing because I think ultimately Laplace is describing an ontic notion, whether a given state fixes the other state. But he's doing it while talking about observers and what they know. And so you might have thought, just looking at it, that he was actually describing an epistemic concept. So hopefully I'm convincing you that there's kind of like this distinction is subtle, and there's a lot of conceptual confusion surrounding these categories. So let me end with this one. What about causality? Yes?
Just one more comment on determinism.
Yeah.
If you're thinking about epistemic, like probability distributions, your state of knowledge or ignorance about the system, why would you even care if that evolves deterministically if you don't know everything about the system in the first place?
Why did Laplace care, or why would anyone care?
Yeah, why would anyone care? It doesn't quite make sense to me.
Well, I think it's just a funny way of expressing something about the actual physical dynamics. So if I say, look, I have some Gaussian distribution over phase space, and I can describe its evolution totally deterministically, right? So I know exactly what I should believe about the physical state in the future, given what I believe in the past. And suppose I can also reverse that. For a given state of knowledge about the future, I can sort of get back what I should believe in the past. Then what that suggests is that my entropy is not increasing. My entropy is being, suppose my entropy is not increasing. And I think my assumption of reversibility implies that the entropy can't increase, because if the entropy increased, I wouldn't know how to get back. I think that's right. So if that's the case, then it has to be that the physical state is evolving deterministically, because otherwise, its final state would depend on some environment, and I would lose information about the system because I don't know about the environment. So I think talking about whether or not the evolution of your knowledge is deterministic can give you a handle on whether or not the underlying physical evolution is deterministic. I think that's why Laplace was doing it, and it's also a reason still to do it.
It seems more economical to just talk about, just take determinism of your epistemic distribution as evidence of determinism in the underlying dynamics.
That's what I'm trying to say, yeah.
Okay.
Maybe I didn't say it very well, but I think many people take that view, yeah. Did you want to make another comment on determinism?
Yeah.
Okay.
So Laplace's definition uses the agent.
Yeah.
But his definition of determinism also seems too restrictive by doing so, because he assumes that even if it's fixed, that it's computable. So to say you have all the data of the universe, then it's still an assumption to say that even in principle you could extract future evolution. Because, well, that's an assumption. So,
Yeah.
and even if you would not have that assumption, even if you would have determinism without even in principle being able to calculate what that evolution would be, I would still say that it's determinism. So that's why it's definition.
So you're saying this is why Laplace's definition is maybe faulty in a way that I think. I mean, Laplace was trying to say not just a being who knows everything, but a being who has unlimited computational power.
And even then, in principle,
Yeah.
There's this field of computability theory that I don't know anything about, but I know that some things in principle are not computable. So I suppose
Right.
something
Right.
like class.
Yeah, it's a good point. OK. Actually, I'll leave you to think about whether causality is an ontic or epistemic notion. I just have a few more things to say before we wrap up. So I want to now give you a rigorous definition, a more precise definition of this this notion of psi-ontic and psi-epistemic invariable models, that distinction. So suppose you take two pure quantum states, psi1 and psi2. And now I'm going to write p sub psi1 and p sub psi2. These now are going to denote two preparation procedures, each one. Because remember, it might be that there are many ways of doing a preparation procedure that corresponds to the quantum state, psi1. So I'm just going to take p psi1 to be some list of instructions of what to do in the lab that you would represent in quantum theory by the vector psi1. OK, so the idea of a psi-ontic model is that it's first of all a realist model. So it assigns a distribution of your physical states lambda for every preparation procedure. And so in particular, it assigns one for p psi1. And it assigns one for p psi2 as well. And the idea is that if psi1 and psi2 are distinct, meaning they're not pointing in the same direction in Hilbert space, so maybe I should have really said non-collinear. They're not the same vector, and they differ by more than just a phase factor. Then the idea of a psi-ontic model is that these distributions should not overlap in that case. So it'll look something like this. So these distributions might not be delta distributions, but if I have two different states, psi1 and psi2, then they're going to be distributions that don't overlap. Yes?
I thought that previously when we were introduced to mu and we interpreted mu, I thought we interpreted that in a psi-epistemic way. So I'm confused about how to bring my previous knowledge of mu to this context. And
So
I thought that lambda is the actual state.
I'm sorry?
I thought that lambda is the actual state.
Lambda is the physical state, and mu is what we know about lambda. So you might call it the epistemic state. And the question now is the set of parameters that are described by psi. So let's call psi, to start with, it's the operational state. So it carries all the information about predictions. And now we want to know, are the parameters in that operational state ontic parameters or epistemic parameters? Which just means that as I vary them, am I forced to vary lambda? Or is it sufficient to just vary mu? Could it be that changing psi only requires me to say I must change my knowledge about the system? Or is it that by changing psi, I have to commit to reality changing in some way? So that's why there's still a sort of a question. We haven't yet resolved the issue of whether psi is ontic or epistemic. And the reason what I've just defined here we call psi-ontic is that if I imagine changing some parameter in psi, okay? So I've changed from some psi1 to some psi2 by varying some parameter in the quantum state. Then necessarily, I've changed from one distribution to another disjoint distribution, right? That's the assumption here, that if psi1 and psi2 are distinct, then the associated distributions are non-overlapping. So that means that as I change that parameter, I have to have changed the physical state, because originally the physical state was something in the support of this distribution. And now it's something in the support of this distribution, and they have no elements in common. So any change in the parameters of psi in such a model involves a change in reality, in the physical state of the system. So that's why we say in these models, psi is an ontic parameter. OK, is that clear? OK, so now the alternative, we can just define a psi-epistemic model to be one that's not psi-ontic. And I'll just go through the definition just to clarify what it all means. So what that means is that there should exist some pair, psi1 and psi2, of distinct states, non-collinear, such that this overlap, these distributions do overlap. So there's somewhere in the physical state space where the product is not zero. So it'll look something like this. And so now the reason we want to say that maybe it would have been better to say something like, psi is not wholly ontic. So it sort of has some epistemic component. Because if I now vary parameters in psi, I vary from this distribution to this distribution. But it's possible to imagine that the physical state was some point in this overlap all along. And it hasn't changed. And so it's possible to imagine that as I vary the parameter in psi, all that's changing is my description of the physical system. I start out by knowing this about the physical state, and I end up knowing this about the physical state. But the physical state hasn't changed. It's whatever it was. And so in this sort of model, you can imagine that the quantum state is only describing your ignorance and is not changing as I change reality. So let me try to say this in one other way, and hopefully it'll make it a bit clearer. Imagine we were talking about properties in classical mechanics. So we know that the complete description of the physical state involves specifying the positions and the velocities of the particles. And then I said, OK, here's a quantity, the center of mass. Is that an ontic quantity? The answer is yes, because every change, so the center of mass is defined in terms of ontic variables. So it itself is an ontic variable. Any change in the velocities and positions of particles can change the center of mass. And any change in the center of mass has to be underwritten by a change in the properties of those variables. And so what we're asking here is, could psi be like the center of mass? It might not be a complete description of the reality of a quantum system. So like the center of mass, there would be some more stuff to say. But it's kind of, there would be a coarse-grained description. So the center of mass really says, oh, look, there's a whole bunch of microstates that all correspond to this center of mass, and there's another set of microstates that correspond to this center of mass, and they're disjoint sets of microstates. So the center of mass is like a coarse-grained physical property of this system. So sort of here we're asking, is psi like that? Is it that there's some deeper description of the physical states of the system, but when I tell you psi, I'm locating you within one of a set of subsets of these guys, and so I'm just giving you a bit of information about what the underlying physical state is. That's what psi is doing in such a model. Or is it the case that psi can't be thought of as a coarse-grained property and must be thought of as describing an agent's knowledge? So here it's clearly not a coarse-grained property of the physical state because it's no longer encoded in the physical state. Here, you tell me the physical state, and you've told me psi. Because for every point in this space, there's only one psi that's consistent with it. Here, you tell me the physical state, and I'm still left uncertain about what psi is. And in that sense, psi must have a epistemic character. OK, so we're basically out of time. I'm going to, I think, get back to this at the beginning. Let's see. Yeah, I'm really out of time. I think you're actually going to see this in the tutorial. Yeah, tomorrow. So I think I'm not going to cover this in lecture. It's available on the wiki. But in the tutorial, you're going to see two examples of some models, which I call the Bell-Merman and the Cauchy-Specker model. And they're just simple examples of a psi-ontic and a psi-epistemic model. And then next time, I think we're just going to talk some more about psi-epistemic models and what they have going for them. OK, see you tomorrow.